In this lesson, we're going to look at rational functions. Rational functions are otherwise known as rational fractions, and they are a type of algebraic fraction where both numerator and denominator are polynomials. This can be shown in different ways. With functions, which you'll study a lot more of, it can be represented by f of x, which would be maybe p over q. Would be a common convention. And we have restrictions. We've sometimes these little extra bits where maybe e is an element of all real numbers, or in this case, q cannot be equal to 0, or otherwise it would be undefined. So we see a few of these examples as well today. So I have 5 examples of rational functions here, and this is just a starter just to see where we're going. If we have a negative number with this particular question in the first one, okay, so f of x is equal to root x squared minus 5x plus 6, we would be led into a different type of maths where we have complex numbers. So it's not going to be negative. That's one thing we know already, one of our restrictions. So here we know already we could use quadratic equation or factorize it. Let's try and factorize it first. So x times x is x squared, 3 times 2 is 6, and minus minus is equal to 0. But in this case it's actually greater than or equal to 0. The minus 2 minus 3 could be in any position. So x is equal to 3 and x is equal to 2, apparently, which in which case it should be x is greater or equal to 0. In this case, x is greater or equal to 3, or x is greater or equal to 2, you may think. But let's do a little test. Okay, let's do a little test. I'll just put in literally like this. No need to show off. I'm going to put between 2 and 3 and test a number. So let's say I test 0, which is less than 2, 2.5, and 3.5. And we plug in those numbers into our x squared minus 5x plus 6. It's kind of called a sign analysis test, but you're just basically testing where things would be positive or negative in this case. And when you do it out, you'll find that it's positive there, negative, and positive here. And you can do this along the way just to check, so that when you do a picture or a graph, we'll say, I should be more specific, a graph, so you have 2 and 3 here, that you'll notice that it's positive. I'll put that in red maybe. We put that as positive here and positive there, as according to our test over here. Okay, so do we find that our domain, so I'll put D for domain, our domain is in fact minus infinity, I suppose, and 2, and our range is 3, positive infinity. Now some of this, if it's not clear so far, we will go into show what they mean in the next few examples. To the right of you, you can see a graph. This is possibly where rational functions were first introduced to you, with a reciprocal graph. So 1 over x. So you may have 1 over x, which would be a constant of 1 and a variable of x. But as you go in through these, you'll find there'll be a lot more complications. You'll have coefficients with variables, so 4x with a square or beyond as well. So operators too. So 4x squared plus 3 all over 3x minus 7, and so on. So you'll have more complicated questions like that. The domain is the possible values, so x values, along the x-axis on the graph per se. And the range are the possible y values of a function, which would be along the y-axis. Okay. Let's have a look at an actual question here. And on the right-hand side, there might be a few pictures. I'll get to them in a few minutes. Second example, so x squared minus 4, all over x minus 2. So what do we do with this? It kind of looks a bit difficult sometimes for students when they first come across it. What I have on the right hand side actually are a set of pictures. We have asymptotes and we have a hole or a break in a graph, which is where we have something that's undefined. The value is undefined there. The example that's actually in the picture is not related to what we're doing, but we will come back to that, okay? So let's check our restrictions, or what we have here in terms of meaning. X squared minus 4 over x minus 2. We know that the denominator cannot be 0. We know that. So x minus 2 is not equal to 0. So x is not equal to 2. And we know that that's a hole. Unrelated to the picture over here, but that's a hole in terms of an undefined part there. Okay, let's just do the same as what we did before. I'll move a little bit more quickly now, within reason. X minus 2 and x plus 2 all over x minus 2, and of course we can cancel out x minus 2 and x minus 2. So we end up with x plus 2. So you may be able to simplify it, maybe, but your domain will not change. And we'll get to that more, the domain and range stuff as well. It stays the same, or basically gets much more complex, or more complex in a general sense. That is just an example of one. I'm just going to keep doing a few. Each example is a kind of a different element to it. And I have a few more. 3x over x minus 4. Again, x cannot be equal to 4. We might be able to tell, you may be able to tell what this is. There's not much more to this one, really. It's a vertical asymptote. If x is equal to, well, x over 0, I suppose, is where we're coming from with that. But you cannot remove, I suppose, the domain issue of that. So we're going to look at vertical asymptotes, which is here, and horizontal in GCSE, iGCSE. In A level, it's pretty much the same. You won't really see that one much, if at all, the oblique asymptote. But we do deal with inverse graphs, even with inverse functions. It won't be the same. Anyway, we just here's a little bit of a different question here, question 4, where we have a kind of combination question. So 2 plus root x plus 1. Again, x minus 1 is greater or equal to 0, so x is greater or equal to, 1. So that would mean a domain. My domain then is x is greater or equal to 1, so it should be 1. So this is the x number to infinity. And what's a range? Well, if you just plug in, your domain, your x value is 1, or greater than or equal to 1, plug in that, and you'll see that you can get your range. So there's a few little tricks here and there, just trying to show basically with these examples, so that you can plug in the value of your domain and find the range. Same with inverse functions. You can do something nice and neat. You see now in this example here. So when we have x plus 1 over x minus 1, same rules apply. Let's put in our little, we know that x is an element of all real numbers. Often that's a very clear one, but the ones that apply here are x is not equal to 1. So our domain in this case, well, x is not equal to 1, I suppose. Let's put that in there. It's a vertical asymptote. I'll put in VA for now. And a range, well, this is what we can do. We can do the inverse, because the inverse of a function, the domain of the original function is equal to the range of the inverse function. So let's multiply across. Y times x minus 1 is equal to x plus 1. And from there, just simplify it all out. So basically what you're getting at the end is x is equal to y plus 1. Oh, I should do it out. We've cancelled some things on both sides. I'm just doing it all out. I think I can just jump now to this next step. So I'm going to move that around. Actually, 1 plus y, I'll put y plus 1. Just to make it look a bit more like the original. And I've already would have factorized that. So y minus 1. I'm presuming you know that already, that stuff. So that is how you can find your range. So that I suppose in this case not too difficult, but y is not equal to 1, but that is a horizontal asymptote. So again, this is a short enough lesson just showing how rational functions may work and how you might just come to terms with some of the ideas involved. Just last little bit, the asymptotes and holes. A hole is like an open circle, I suppose. When you've done your number line before with inequalities, you'd have an open or closed circle. So that's maybe somewhere else we might see it. It's a hollow open circle. It's a point where the function is not defined. So where y is equal to 1, the function is not defined at a point, but it does approach it. It approaches on both sides. It is not in the domain of the function. It's not part of the x values, we say. It shares common factors shared by the numerator and the numerator and denominator, or both, as 0 even. And asymptotes, again, if you want another example of that, just think where tan, theta, we have just, I'll go into the trig identities just quickly here. We know that cosine cannot be 0 in this case. And we know from the graph of cosine, quick little sketch, we know that for instance, a tan, let's do tan as well. So tan goes through 180, there like that. Okay. And we know that asymptotes are on tan at 90 degrees and 270. And where is cosine equal to 0? Well, cosine is equal to 0 here and there at 90 and 270. So that just gives you another maybe idea into that expansive way that this works. Of course, it all makes sense eventually when you learn, advanced algebra and geometry. So there's a few little ideas. Hopefully that helps. And of course, you need to go into a little bit more depth with the domain and range on the A-level course especially. But for GCSE, this should be enough just to see how this works.